Hello. Today I will talk about Turing instability and pattern formation in reaction diffusion system. So I am Shubhadeep from IIT Kanpur. Uh, we can see the patterns are everywhere. You can see different patterns on different animals. Like you can see here that zebra patterns and cheetah also have some pattern of black spots on their yellow skin. So this was the first motivation to work in pattern formation, and this work was mainly done by Alan Turing, and I have talk about the Turing instability in my title slide. So that is in the name of Alan Turing. Okay. So what are the uh, what are the what can be the model for this pattern formation we will study here. So first the question, the patterns are what? So patterns are spatially non-uniform. So it will be just somewhere black, somewhere it is yellow, somewhere. So different kind of species have different concentration in different spatial points. Okay, and it is steady in time. Steady in time means it will not change with time. So these are patterns, and we are talking about the steady patterns. There are temporal patterns also, but we are talking about steady patterns in this talk. So, and what is pattern formation? Pattern formation is the transition from a spatially uniform to a spatially non-uniform solution due to the instability. And instability of what? Instability of the former solution, that is the spatially uniform solution. And as the spatially uniform solution is unstable, so it will not go back to, if you perturb the system, if you perturb the concentrations of pigments or morphogens, it will not go back to the uniform spatial pattern. Not pattern, actually not pattern, basically non-uniform. So uniform spatial pattern doesn't make any sense. So we will get some non-uniform spatial pattern. And what is Turing instability? And actually it is happening due to the Turing instability. I will discuss in my whole talk about this, that the dynamics of the concentration of two species shows a uniform solution, spatial solution, which is steady in time and it is stable. Now if you introduce diffusion, it can make the uniform spatial solution unstable, and as it is unstable, it can give temporally steady and spatially non-uniform solution, that is pattern. So we can get pattern due to this diffusion driven Turing instability. So in our this motivation of this talk will derive, and what are the conditions on the diffusion rates to get the pattern in such system. So we need to derive that. Now just think about system of two reactants. So one is U and another is V. Their concentration of two reactants and their dynamics is given by these two equation. Okay, so du dt is equals to some function of u and v, and dv dt is also some function of u and v. We can discuss the form of f and g in detail with the explicit dependence on u and v in detail after doing the general treatment. So fixed point is given by u star v star such that f u star v star is equals to 0 and g v star u star v star is 0. So that means the rate of change of these concentrations are 0, and if the rate of change is 0, then it will not change in time. So they are fixed in time, so that is why it is called fixed points. So Now if we part of the system, that means we disturb the system a little, then we can just write our solution like this: u is equals to u star plus some delta u, and v is equals to v star plus some delta v. So delta u and delta v are the perturbations, and it is around they're very small perturbation, and it is around your fixed point u star and v star. So then if you just expand the solution in Taylor series and about the fixed point, you get the dynamics of your perturbation, and your dynamics of your perturbation will be in this form, that d delta u del dt is equals to j, which is a matrix multiplied by a column matrix. This delta u is basically a vector, and it can be represented in column matrix, where you can see that delta u is equals to delta u delta v. The delta u vector is, and this j is called actually Jacobian matrix. So this Jacobian is elements are f small u in subscript. So this subscript means the partial derivative with respect to u, and if it is, so the subscript is v, that means the partial derivative with respect to v. So this is our notation, and this is calculated at u star v star, so at the fixed point. So we have kept the up to the linear term of this perturbation. We can have, actually in reality we can have more terms, but we are doing linear stability analysis, so we kept only up to the linear terms. So there will be some delta u square terms, but as I have told you that delta u is very small, so delta u square will be very small compared to the delta u, so linear term will work for us, and it will tell the correct result, at least in the local sense. Okay, now the condition for the stability. So you can just reduce this equation, you can just reduce this equation to some eigenvalue problem, where you can just analyze the eigenvalues of j, and your according to the sign of the real part of the eigenvalues of j, you can say that the solution will be stable or not. So for stability, what we need, both of the real part of both of the eigenvalues will be negative, and for that what we need, the trace. So trace of the matrix says about the, as it is a 2 cross 2 matrix, so trace of the matrix will say the addition of two eigenvalues, and the determinant will tell you the multiplication of two eigenvalues. So as I need the both of them negative, so the trace will be negative, because if you just have even imaginary eigenvalues, then the imaginary part will cancel out, and because all of them are real coefficients, so the imaginary eigenvalues will be in conjugate. So one of them will be, if one of them is a plus ib, then another will be a minus ib. So, and delta is the determinant is the multiplication of two eigenvalues, and if both of them negative, then it will be positive, because it is multiplication negative. So this is the condition for stability. Now I am assuming this spatial uniform solution. This is spatial uniform because there is no space dependence in u and v. So in spatially uniform solution is stable. Let me assume that. So I am assuming the trace is, this tr is negative, and this delta, the determinant, is positive. And what if I introduce diffusion? So let's see. Now I allow diffusion for both of the species. Now the dynamics are given by, so this blue part is whatever it was, and now I have introduced du delta square u and dv delta square v. These are the diffusion terms. So now this equation actually tells you this blue part is the reaction part, that is the non-linear. It can be in general non-linear. So f and g can represent the reactions, and depending on the concentration of two species, how the rate of production of u and v will change. So that is the reaction part, and this is the simply diffusion part. So that is why it is called reaction diffusion system. And now you can easily see that if we had a uniform spatial solution, that's u star and v star, so that is also a fixed point for this reaction diffusion system, because the u star and v star has no spatial dependence. So if you put here, so it will be 0 and it will be 0, because it was the fixed point for the system without diffusion. And with diffusion, as diffusion is just spatial derivative, it involves spatial Laplacian. So Laplacian operates on some constant value, it will not give you anything other than 0. So at u star v star, this will be the right hand side of these equations will be 0. So this is again the fixed point, but now this fixed point will be unstable and some non-uniform stable solution will occur in space. So we want to discuss about the instability of this uniform spatial solution. So now our perturbation form is delta ut and delta vt is, so u tilde multiplied by exponential of lambda t plus I k dot r. So basically you can see that this is the growth term, that with time it will grow or not. So this lambda, if lambda is positive, lambda is basically the, in the last part, in the previous part, what I have told about that Jacobian, and lambda is basically the eigenvalue of the Jacobian. So if it is positive, then it will grow, the perturbation will grow, that means unstable, and if it is negative, then it will decay the perturbation, and this will be stable. And now I k dot r, it is the basically the spatial dependence in Fourier transform mode. Okay, so it is the just Fourier transform of that part. So now what is the condition for instability? So now we will do analysis with diffusion. So expanding the variables again in Taylor series about the fixed points, we get the dynamics of perturbation expressed as this. So now this Jacobian is slightly modified because this JD is with the diffusion. So now diffusion terms are there in JD. JD means D means with diffusion. So again, if you calculate the at the fixed point this Jacobian matrix, then it will give you the in this form, and the Jacobian is basically modified by minus k square du. Du is the diffusion coefficient for the u species, and dv is the diffusion coefficient for the v species. And this is the form of Jacobian with diffusion. Now the trace and determinant of JD are given by this trace TRD is equals to trace of JD, and you can write it in terms of the trace of the Jacobian without diffusion, this TR, and minus this k square du dv, and this delta D is the determinant of the JD, and it can be written as this. Now you can focus on this trace term. So what was my trace? The sign? This was negative from the analysis without diffusion. Now trace is negative, and this minus k square du plus dv. So du is positive, dv is positive, k square is positive. So du is a diffusion, so it must be positive. So this term is totally positive, and in front of it there is a negative sign, and it is another negative, so it must be negative. Trace must be negative. So it is not possible to have two eigenvalues and both of them positive. But for instability we need at least one positive eigenvalues. So for that we can, if we have just our determinant is, if determinant is negative, then it will be, yeah, sure, if determinant is negative, then one of the eigenvalue is positive, one of the eigenvalue is negative, and it must be, because if both the eigenvalues are imaginary, then delta D will be positive. But we are not talking about the imaginary eigenvalues, because it will give some temporal solution also. So temporal oscillations actually. Yeah. So now if you focus on this delta D, you can see this again, this term is positive, the du is positive, dv is positive, k to the power 4 is positive, and this delta is positive because from without diffusion analysis. So we, in terms of, in order to make this delta D negative, we must have this positive, this green part is positive, then it can be its magnitude can dominate over these two terms, other two terms, and it can be negative, then in total this delta D can be negative. So now this will be our necessary condition, because if it is positive, then it may not dominate over other two terms, and it may not lead to some instability. It is the necessary condition for this, and this is the necessary condition for this. But when it will dominate over these other two terms, then it is the sufficient condition to have instability, because this is negative. So that means what? The multiplication of two eigenvalues is negative, and that tells me one of them is positive and one of them is negative, the eigenvalues. So now we have this, the trace of without diffusion, the trace is negative, that is fu plus gv. Now two cases are possible, the both of the terms are negative, and any one of them is negative and another is positive, and whichever is negative, that magnitude must be larger, because then it will be this condition will be satisfied. So this k square, this term, in the last slide I have shown this term, this k squared multiplied by fu dv plus gv du, this cannot be positive for the case A, because in case A both of them negative and other all terms are positive, so this will be negative, so this cannot be the case. Now case B must be our case, and it may show instability. So now let us just assume that fu is greater than 0 and gv is less than 0, and this is just a convention, you can just take it other way around, because we have not say which one is u and which one is v. So actually this has some physical meaning, I will come to this later. and you can just relate that why it is positive and why it is negative. So and the magnitude of fu is lesser than magnitude of gv, because I have told that to satisfy this condition, this stress is negative, that if it is as fu is positive and gv is negative, so gv must be larger in magnitude, then it will be negative, lesser than 0. So this leads to a necessary condition for instability, and which is given by this, that as gv is negative, that means what, this part must be greater than the second term. So magnitude of fu dv must be greater than gv du, and this leads to dv divided by du greater than the magnitude of gv by fu, and which is obviously greater than 1. So this is the necessary condition but not the sufficient condition, because it will ensures that your this term will be positive, but it is not ensuring that the other two terms in the expression of delta d, it is not dominating over the other two terms. So when it will happen, then the total delta d will be negative, and it may cause instability. It will cause instability, not may even, it will cause, and that will be the sufficient condition. So let me analyze this. So now you can just write down the determinant delta d with diffusion. Basically it can be plotted with k square to have more insight. So you can just check it out, that determinant of jd is delta d is equals to, it is a parabola in k square, right? So if we plot this delta t with k square, it will give some parabolas. Now your set 1, set 2, set 3 are basically some parameter set I am talking about, and you can see that for some set it is, but basically this black line is basically 0, delta d is equals to 0. So below of that line is showing some negative value of delta d, and above it is positive. So as this is a parabola, you can see that it will not go anywhere. So this is the minimum, only one minimum is there. Okay, so it will not cut anywhere somewhere else here. So if you just extend this axis and it will cut, no, it will not. So as it is parabola, it can cut only 2 points, and when it will be like this, so this is the just marginal, okay, it is just touching the 0 line. But when it is for set 3, it is like this, then you have some range. So these two are basically solution of this. So if real positive solution exists for k square, then there will be a range for which this delta d is negative. So this is the range I have just shown with this red curly bracket. So one of them is k square 1 and another is k square 2. So you can just have this range for which this delta d is negative, and if it happens, then that means this is the sufficient condition to have instability. So now for this you can see this okay, so this xi is positive, because we have just proven that it must be positive if we have this necessary condition satisfied, then it is positive. Okay, now this du dv and delta is also positive, so this square rooted term is lesser than basically xi. So we can have two k square values, which is real solutions, and solution means it is cutting this x-axis, basically k square axis here. So we can have the solution when the square rooted term is positive, the inside the term inside the square root. So this is the sufficient condition. Okay, so this xi square, and which is actually xi is depending on this diffusion coefficient and the system parameters also, and obviously system and system parameters. So because this fu and gv is there. Okay, so now this is the sufficient condition for instability. Now we have presented that what is sufficient condition and what is the necessary condition for this instability. Now I will talk about a very funny thing, that when about activation and inhibition. So just think about, there is a forest and some forest fire taken places. Okay, now what if I have now what I will do, that people will just try to uh, kill the fire, and they will put water from helicopter or something else for the forest fire. Now we need to go faster, so water supply need to go faster than the fire. Otherwise what will happen, that fire will take over all the forest and it will totally burn. Okay, so if it is totally burnt, then what will happen, we have just only some black ash basically. Okay, so we cannot have any pattern. But when your helicopter is going faster than the fire, then it will basically, it will be able to kill the fire before it get the whole forest. So there, in that, by that time the fire will catch some places, in some places, and there will be some pockets of burnt forest. Okay, so there will be some places where fire is there, some places where it have not taken any fire, and it is basically as it is. So there will be a pattern on this forest. So you can see here, some places are burnt, some places are still green there. So there will be some pattern. So this is the same case is happening here with our this u and v. So whatever we have taken as u, so fu is basically telling us, f is the rate. Okay, so df du is telling us that if we increase the concentration of u, then what will be happen to the rate of increase in, what will be the rate of, how it will change, the rate of the change in u will change. Okay, so if we increase the amount of u, then if fu is positive, that means it will produce more u if you increase u, and gv is negative, that means if you put some v, then the rate of production of v will be lesser. So that is the rate of rate basically. So the first u, which is basically increasing, if they itself increases, then it is called activator, and another is called inhibitor. So it inhibits that. So as we can have the as a necessary condition that the diffusion rate must be faster for the v. So dv was greater than du in our case. So inhibition is faster. So here also you can just compare, don't compare literally, but compare as fire as activator and the fire armies are basically inhibitor. This is basically water. So water is inhibitor, it inhibits the fire. So it is the must condition, necessary condition for our pattern formation. And you can just have an example. Okay, this is a you can have an example, easy example to understand it, but don't compare it literally. But this is the case, this is why we have this kind of necessary condition. Now we have taken a simple example to apply this theory. This is a Brusselator model, and the model is given here, that because the functional form of f uv and g uv is the important for us. So if you take this fuv and guv in this form, then the fixed point is given by u star is equals to a and v star is equals to b by a. Now just fixed your parameters. A is equals to 2. I have taken this, you can just take another something else. So a is equals to 2, b is equals to 4, and du is equals to 1. Now we have to choose what will be dv, because we have other conditions. Now dv must be greater than 1. This is a necessary condition, and for sufficient condition we have just plotted this discriminant of that k square solution over dv. So if I change dv, when it will be positive. So I can see that around 4 it is, after that beyond 4 it is basically positive. And we can have as it is positive, then this in this regime if we take dv, then we can have patterns. So I have taken here dv is equals to 5, such that both the necessary and sufficient conditions are satisfied. Now we are ready to have patterns. Okay, so this is a simple numerical solution. I have just used Euler time forward scheme for this, and we can see this spot pattern here, u and v both in just the values are different, and this is in 2-dimensional domain. You can have it in 3 dimension, or but in 1 dimension it will be very trivial, like oscillatory only. So and I have taken the initial condition as just some random perturbation about the initial uniform solution of 2, 2. So I have just taken the random perturbation as initial condition, and periodic boundary conditions are taken here with nx is equals to 64, ny is equals to 64. These are the basically grid size, and I have just using this time stepping of 0.01, and final time is 2000. So you can have this kind of patterns with this, and you can have a lot of models and a lot of things available in literature. And the parameters are also can be taken, like if you do some analysis, more analysis, nonlinear analysis, you can may predict the sum that what will be the nature of your patterns. So for this context, that to understand how pattern forms, that these are not necessary. For now we have understood that how this Turing instability have taken places, and how we get these patterns. Okay, so now this is the time to conclude. This is a simple study of reaction diffusion system to understand how steady spatial pattern forms. Diffusion can lead to a spatial pattern even when a stable uniform solution exists, when diffusion is absent. So in the normal sense, what we think about diffusion, the diffusion basically, when we have some non-uniform concentration, it makes it uniform. Suppose somewhere else, some in some corner of your room you have some fragrance, okay, but after some time it will the particle of the fragrant whatever fragrant molecules, so it will diffuse to the whole rooms and it will try to uniform, make it uniform, okay, the concentration of the that molecules will be uniform in your room. But here diffusion is doing something counterintuitive. We have some uniform concentration and diffusion makes it unstable and it is giving some non-uniform solution, and this is really interesting. So we have derived this necessary and sufficient conditions for the spatial pattern, and this is the necessary condition and this is the sufficient condition. So and we used finally a Brusselator model. We have just taken it and do the linear stability analysis and finally observe the spatial patterns in computer simulation, and that's all. Thank you.